Okay, so the second part of chapter 33 will be about some hardcore physics. So just pretend you just listen to some stories. Okay, it's fine. So it won't be appear in the exams. So first part is about the magnetism of the Earth. Okay, so of course even a child know that. Okay, we can use a compass. To know which direction is north or south. So actually, the Earth can generate. It's actually a big magnetic dipole. Yeah, but actually, So the magnetic North Pole, South Pole. And actually the geometric North Pole, South Pole are not the same. So it will be like for the Earth. Okay, so of course we have the geographic North Pole, geographic South Pole. So according to the rotational axis. So actually, okay, so we have a sun in the middle, and then we also have the Earth, okay, and then this rotational axis is actually not 90 degrees to this plane, okay, it's like side tilt, so that for the Earth, we have 4 seasons, or at least 2 seasons. We have summer and winter. Yeah, because sometimes we are closer to the sun, but sometimes we are not. So to make the weather difference. And actually, for the magnetic North Pole, South Pole, or we will say it is a geomagnetic North Pole, geomagnetic South Pole, are not allied with the geographic North Pole. Yeah, because when we talk about North and South, we always talk about the geographic North Pole and South Pole. So which means that okay, they are not the same. So, and I should say that if you need to buy a compass in this place, okay, or in that place, okay, they should be adjusted to different angle. Okay, so they need to be adjusted. Okay, they need to be adjusted. So that, okay, so if you are far away from the North Pole and the South Pole, okay, it will be more accurate. Yeah, because they are very far away, and then even though it is a little bit off, then it is still fine. Yeah, but actually, I'll say it's not perfect. Okay? It is not perfect. They can never point to the perfect north direction or south direction. Yeah, especially if you are near here, and then the compass can tell you the correct stuff. So of course, in that sense, of course, we need to rely on the GPS or something like that. Yeah. Anyways, for the magnetic field generated by the Earth, okay, of course we can be able to know roughly the direction, but another most important function of this magnet, okay, is it shields the Earth from the high energy particles. Okay, if the Earth won't have this big magnets, okay, so all of us will die. So the idea here is so of course in the space, okay, there are quite a lot of high energy particle. They may be generated by some of the black hole, but generated by some stars, whatever. Okay, 就是那些什么中子星啊什么之类的，也许它们的重力会产生一些高能的射线。Okay, so in that sense, there are quite a lot of high energy particle. Of course, this high energy particle shooting to the Earth, not that much, but yeah, it's quite a lot. Okay, so it can be a certain amount of that. Okay, so and of course, this kind of high energy particle are charged particle. So in that sense, just imagine if there are some particle, okay, going from this direction, okay. So here, suppose we have the B field, okay, generated by the Earth, and then okay, so this is a moving charge. Okay, let's assume this is a positive charge. Okay, I don't need to care about. Okay, so it doesn't really matter. It's a positive or negative. You just go opposite direction only. So the idea here is if it is a positive charge, okay, so we have this V pointing, let's say pointing to the Earth. Okay, if so, we don't have this B field directly shoot to the Earth. Maybe shoot some of us. And then, okay, shooting by this high energy particle may cause cancer. So this is not good for us. So that's why I said if the Earth won't have this B field, okay, all of us will die. But hopefully we have this B field. So in that case, okay, so for example, at this point, okay, the B field points to this way. So I hope you still remember the Lorentz force. Okay, so Lorentz force is V cross B. So the V points to this direction, and then the B points to this direction. Okay, so in that case, yeah, there should be a force acting like this. Okay, so which means that it is like, okay, so the particle shoot to the Earth, but okay, so there's Lorentz force. Okay, so make it like turning around. Okay. Turning, yeah, not perfectly turning around, but at least it is shielded. Okay, so shoot to the other place. So that, yeah, so that's why we call it a shield. Okay, it's called a shield. So just block it out. Okay, but there are two weakness. Okay, two weakness. Okay, the two weakness are here and here. Okay, near the North Pole and the South Pole. So you can simply imagine that if there are high energy particles shooting from here to here, okay, so of course the V is in this direction, and then the B field are like more or less opposite direction. So, so you know that V cross B is like V times B times sine of theta. So if this theta is close to 180 degree or close to 0 degree, if it is from this side, this theta will be close to 0 degree. Sine of 0 degree, sine of 180 degree will be close to 0. So in that sense, this force will be weak. So there's, in that sense, the particle will shoot to these two weak points of the Earth. So of course, this is also close to the North Pole and South Pole. Maybe one of it is near the northern Europe, and the other one is near the South America. Okay, so actually we can actually see the aurora in the northern Europe or the Southern America， 就是你如果去北欧的话，可以看到极光。那些极光的话，其实就是那些高能粒子打到那些空气了，打到空气，然后它电离所以产生那个极光。所以很多的话，它就会产生比较多的极光。如果很偶尔一粒两粒的话，你就看不到因为那个。本身可能有太阳，或者是就算黑夜的话，如果只有很弱的一颗两颗的话，你也看不到。但是如果很多的话，它就会有极光现象。所以极光的话就是，如果它电离了那个粒子，那当然的话，它就会吸收掉那个能量，那就还好。但是如果没有吸收到的话，那就会被下面的人吸收，所以住在那个区域的人就比较危险一点。 Okay, so this part is another, so actually the most hardcore stuff in the physics that I've learned. So actually it is called the spin, okay, the spin magnetic dipole moment. So the question is, okay, the charge will generate E field. So what will generate the B field? Okay, so before we know that, okay, if we have a static current, we will have B field. Okay, we have let's say we have a long straight line current, then we will have a mu 0 I over 2 pi r. But what is the fundamental B field that we can achieve is that if we have an electron, we say that it has an intrinsic angular momentum called the spin angular momentum. Okay, so actually in high school chemistry class, probably you have learned something called the spin, okay, plus half or negative 1/2， 就是那个电子的自旋，就是电子的就是粒子的4个什么量子数嘛。量子数，其中一个是自旋，正1/2、负1/2。Okay, so this is called an intrinsic angular momentum， 内在的。Okay, so quite philosophy， 内在的角动量。OK， 内在的角动量就是这个电子在自旋你怎么知道它在自旋？如果一颗篮球在自旋的，在旋转的话。那你就会看到它的纹在动，但是那个电子的话，其实我们看不到它在旋转。但是问题是我们看到它，如果它旋转的话，它会产生一些磁场，所以我们是透过观察到那个磁场，所以我们反推回去说它应该在旋转。Okay, so actually, that's why we call an electron has an intrinsic angular momentum. So all the electrons are actually spinning. So, and then they has an intrinsic angular momentum. And then in that sense, okay, so this angular momentum mu s is actually s. And then E times negative E over m. Okay, of course E is 1.6 times 10 to negative 19, and then mass is 9.11 times 10 to negative 31st. So it's just the charge to mass ratio. And then what is this S? Okay, what is this S? Well, this S is, okay, so S is a very strange variable. Okay, so actually it tells you that we can only measure this S along a certain axis, like z-axis, x-axis, y-axis, or whatever axis. When you try to measure this S along a certain axis, in this case z-axis, so this sz can only take some discrete value. So they are called quantized. Okay, they are quantized. So which means that it can only be mu s times h over 2 pi, and then this ms can only be plus or minus 1/2. OK， 就是那个自旋的正1/2、负1/2，它不是随便乱变的，不能够随意说我要正1负1，我要正2负2。它是透过这个解这个 Schrödinger's equation. So actually we come up with this quantum number, for a particle from the Schrödinger's equation. Of course, we will not cover the quantum mechanics in this semester. But actually, we need to solve the Schrödinger's equation with the hydrogen potential, and then also we need to consider the relativistic effect. Relativistic effect, OK， 就是要在解这个Schrödinger's equation， 然后也考虑这个相对论的效应的情况之下，才会有第4个量子数。如果只是解这个 Schrödinger's equation， 只考虑那个氢原子的那个potential 的话，它只有前面3个量子数。虽然解这个我已经看不懂了，它有一个很复杂的级数，所以再加上 relativistic 的话，其实我还没看过它是怎么推导的。反正它就是告诉你说，解完那个是一个叫做 PDE， 那个是叫做偏微分方程。偏微分方程的话，它就会比那个解这个长微分方程我们的 ODE 会复杂。那解 PDE 的话，一般它会有一些叫做 boundary condition，boundary condition， 就是一些叫做边界的条件啊，就好像说你弹吉他，你有好几根弦啊，每根弦的话，它前端跟后端是固定着的，是绑着的，然后你弹的话，它前后两端是不能动的，中间可以震动，但是前后两端是不能动。它这是有一些这样的条件，让它的解它的话，它只能够有一些 mode， 就是有一些 fundamental 的 frequency， 有一些它的 harmonics， 它就不能够是随意的数字，所以它的话，它就是解出来的话，它就会有一些量子化的现象，就是简单来说是这样的话，那复杂来说的话，它就是解那些偏微分方程啊。那我也看不懂它在解什么，因为那个级数的话，就是我上课的时候他也没有说，他就是告诉你说，哦，他那个解的是那样啊，但是不知道怎么解。Okay, so anyway, so this is just to say that, okay, so this one when we try to measure it, okay, it will have take a discrete value. Okay, so this ms plus or minus 1 multiplied by the h over 2 pi. H is called the Planck constant. 6.63 times 10 to the negative 34, called the Planck constant. And actually, this h over 2 pi is always occur in the I say often occurred in the formula in the quantum physics, and then actually they will divide another notation. Okay, h with a bar. Okay, h bar. They will call it the reduced Planck constant. Reduced Planck constant. Okay. So because it often occurs, okay, they don't try to write h over 2 pi very often. They just want to write h bar, okay, so to simplify the equation. So it turns out to be like equals ms h bar, okay, so easier to read. Okay, so anyway, if you plug in this thing into here, okay, it turns out to be like E times h over 4 pi m, and then this one we call it the Bohr magneton. So it is like something like the unit of the magnetic dipole, okay, of the magnetic dipole that you can achieve. Okay, so this is like a unit, the unit magnetic dipole moment. Okay, that you can achieve. Okay, so beforehand, okay, we just consider, okay, we have a current loop, and then it will generate the mu to be NIA. Okay, but this is a macroscopic view， 这是比较宏观的现象。但是如果你最 怎么说，就是最小的一种情况的话，就是电子自旋所产生的这个 dipole moment， 它可以达到这么小。Okay, so this is the case, and then so the energy. Okay, just some similar stuff. And then the other case is called the orbital magnetic dipole moment. So because we know that we also assume that the electron are rotating around the nucleus of an atom, so that in that case it is also like a current. Okay, so because there's a charge. Okay, charge movement is actually like a current. Okay, so in that case, we call this one the orbital magnetic dipole moment. For the previous case, is the spin angular moment or the spin magnetic dipole moment. Okay, so in that case, we can also have this thing, and then I'm not sure whether you still remember what you have learned in the chemistry, high school chemistry. ML can take 0 plus or minus 1 plus or minus 2 and so on and so forth. And then this one is also the H bar, so also you can write it as a ML H bar, something like this. So, and then this ML can only take integer values, so that it is also a quantum number. It's also a quantum number. So in that case, so if you just plug in this thing to there, and then you can also get something like this. Okay, yeah. So I don't try to dive in too deep into that one. Yeah, because it's related to the quantum mechanics. We don't really want to talk about those quantum mechanics stuff. Yeah. But just try to let you know that, so the physicians try to consider things like that. Okay, so we know, a macroscopic phenomena 就是一个比较宏观的现象。他就想说，它更小可以怎么样 just like they have some element, so they try to find the fundamental particle, like, so in high school, or maybe for primary student, or probably high school, you know that there should be something called the atom. So the physicians try to know, for an atom, where can we break it into smaller pieces? So also in high school, you know that an atom can be separated into electron, proton, neutron. And finally, the physician also try to ask, whether this particle can be even separated into smaller fundamental building block. And then, just as what I mentioned before, the proton and neutron can be even separated into quarks. Although they cannot exist too long. But for the electron, it is at least the standard particle. It is at least one of the standard particle. So it cannot be separate. So anyway, so this is some of the hardcore physics stuff. I've let you know. So and then this is the final part of this chapter. So and then it tried to mention three of the magnetic material. Three of the magnetic material. The first one is called the diamagnetism. 叫做中文叫做抗磁性。抗磁性。So this is one of the most most interesting material that we covered. So here it says diamagnetic material placed. So if we place a diamagnetic material in an external B field, so it will develop a magnetic dipole moment opposite to the B external. Okay, in that case, the field is if the field is non-uniform, the diamagnetic material is repelled from the region of a greater B field towards the region of a lesser field. OK， 所以简单来说的话，它就是会跟外部的磁场会排斥，会 repel。OK， so this is called the levitating fork。OK， 它是一种青蛙，它是一种青蛙。And actually, this research got the Ig Nobel Prize. Ig Nobel Prize. You know the original Nobel Prize, 就是诺贝尔奖啊。And this one is called the Ig Nobel Prize. 中文它叫做搞笑诺贝尔奖。搞笑诺贝尔奖，所以这个研究是拿到这个搞笑诺贝尔奖。这它怎么搞笑的？ So actually, this frog has some material that is diamagnetic. 这个青蛙有一些抗磁性的物质。So the frog is diamagnetic, as is any other animal. So the researcher picked this one, okay, because this frog is light, okay. And then when the frog was placed in the diverging magnetic field near the top end of a vertical current carrying solenoid. So the idea here is like, so this is a top view. So it is like, okay, we have a solenoid, and then we have some current going through it, so that it will generate some, let's say, B field towards this direction. And then we place a frog here, okay, on top of this current carrying coil, so that every atom in the frog was repelled to upwards, away from the region stronger magnetic field at that end of the solenoid. So the frog moved upward into weaker and weaker magnetic field until upward magnetic force balanced the gravitational force on it, and there it hung in mid-air. 所以意思是，也许一开始的话，他就把这个青蛙放在这个中间，先不通电，所以他就站在底部。然后通电的话，这个 solenoid 就会产生这个 B field 嘛。然后这个 B field 的话，就会跟这个青蛙的抗磁性物质去排斥。那这个线圈比它重的话，它就会排斥的话，那这个青蛙就会浮起来。那浮起来的这个力就会跟它的重力去抵消，然后所以它就浮在半空。那这个研究就拿到这个搞笑诺贝尔奖。So the frog is not discomfort because every atom is subject to the same force, and thus there is no force variation between the frog. 所以他说它就没有什么不适的现象，因为它身体里面的物质都受到同一个力的作用，它没有受到一个很大的不同的力，就是如果头跟脚受到不同的力的话，它等于说这边拉得比较用力，那边拉得比较小力的话，它就会被扯住，就是好像说，如果你看那些什么，那些讲什么黑洞的电影的话，它就是说，它有一个叫做spaghetti effect， 就是那个黑洞的话有那个 spaghetti effect 的话，就是假如说一个人被一个黑洞去吸引的话，那就会被异粉化，OK， 意思是人就会被扯成跟异粉一样。拉成一条，因为你头跟脚受到那个黑洞的吸引力的话，就会大到把人拉成一根很长的线。OK， so I think this paragraph just like to point out this stuff. Okay, so this is the diamagnetism. Okay, so and the other one is called the paramagnetism. Okay, so this one is called 顺磁性。 So of course this is just the opposite to the diamagnetism. Okay, so it is actually the opposite to the previous one. So the paramagnetic material placed in an external B field develop a magnetic dipole moment in the direction. Okay, so for the previous dielectric material, diamagnetic material is develop a magnetic dipole moment opposite to the external B field, but this one is in the direction of the B external. So if the field is non-uniform, the paramagnetic is attract. Okay, 所以它们就会吸引towards a region of a greater B field from the region of a lesser field. Okay, so this one is related to this so-called the magnetism. The magnetism. Yeah, so this one is called the Curie constant. Curie constant. Okay, so of course this one is found by Marie Curie. Marie Curie. Okay, when I was small, the textbook just call her Mrs. Curie, Mrs. Curie. But now we need to be more political correct. 我们要追求那个政治正确的话，现在的话就不叫她居里夫人，她就叫做玛丽居里，玛丽居里。Okay, so actually this, so I think, I'm not sure whether you have learned Marie Curie in some of the passage during your high school or even primary class. So yeah, if you have, you already know that Mrs. Curie find the material that can so to generate this so suppose we have some external B field applied to this paramagnetic material. It will also have the magnetization. Okay, so and then actually she proposed that, okay, so this magnetism is like proportional to the external B field, so that the Curie's law is something like this. It's just a straight line. But actually, later on, when we try to measure more, okay, if this B external over T is not large enough, okay, so actually this part actually obeys the Curie's law. But this graph tells you that if B external is higher and higher, okay, higher and higher, goes to that part, it does not follow the Curie's law anymore. It will saturate somewhere. And then actually this part we need to explain it using the quantum theory. Of course, I don't really know what it is, but the idea is like, okay, so for the classical physics, okay, so for simplicity, we just use some simplified stuff, and if we don't have some extreme case measurement, and then okay, we will say those laws are accurate enough. But if we go to some extreme case, if we can increase the B external to even larger value, then okay, so in that case, okay, that law won't fit anymore. Just like for the Newtonian mechanics, if the speed is not high enough, then all the thing will be okay. But if the speed is really, really high, then we need to consider relativistic effect. 就是那个牛顿力学的话，如果你的速度不够高的话，那其实它的比如说算出来的那些动能啊就没问题的。就是比如说动能是什么 k 等于1/2 mv 平方，那如果你的速度不够快的话，那个是正确的。 但是如果你的速度很快，比如说你的速度是比如说1/10的光速，那流动力学就不对了，那你就考虑那个相对论的效应。那个 k 的话，我没记错的话，它就是伽马减1的 mc 平方。如果我没记错的话，那伽马是什么？伽马是一个1除以1减去 v 除以 c 的平方，所以这个 v 如果比较大的话，v 比较大的话 ，v 除以 c 的话就会比较接近1，v 因为 v 不可能超过 c 嘛，那1减去这个 v 除以 c 的平方的话，它就会很大啊，它就会很大。OK， 所以这个就是那个情况。那总能量1的话，它就会等于伽马 mc 平方啊。这是小学生的话就会知道哦，E 等于 mc 平方，那是什么？那个是质能变换的公式，就是跟那个核能有关。就是核能的话是怎么来的？就是它透过核反应的话，它就是失去一些质量，换来很多的能量。Okay, so yeah, I think I will skip this sample problem. I don't think it's related to our stuff. So anyway, final thing is called the ferromagnetism. I think it's the most interesting stuff. Okay, related to us. It is called 铁磁性. Okay, so it actually means that if for the ferromagnetic material can be aligned by external B field, okay, and even though this E field is removed, it remains partial, okay, it remains partial aligned with the region. 所以前面那个顺磁性的话，是你外面给一个磁场的话，它也会产生一个磁场跟着你的方向。但是如果你拿掉的话，它就会消失。这个铁磁性的话，就是你如果外面给一个磁场给它，它会顺着这个方向 ，in the direction of the B external. But even if you remove， 就是你拿掉这个外部的磁场的话，它也会维持这部分啊，所以它就是有记忆咯，它就是有记忆了。那有记忆怎么办呢？有记忆的话，我们就可以拿来使用。简单来说 ，this one is called the hysteresis loop， 这个叫做磁挤效应哦，磁挤效应什么意思？就是一开始我假设它没有磁性，然后我外部这个是一个我想一下，这个是外部，这个是外部的 external 的。Okay, so this one is the external B field, external B field. Okay, so this is the B field generated by this ferromagnetic material. Okay, so if we try to increase the external B field, of course this Bm also increase in some sense. But if you try to reduce it back to 0, okay, so this Bm is still have some value, okay, still some positive value. So you need to make this B external to turn to the opposite side for some value so that you can make this Bm back to 0. Okay, so this is an interesting thing. So this is not like okay, you have a line like this. Okay, you cannot say okay, so at this moment B is a certain value, then we know what Bm is. It relates to what is the status before. Okay, so in that case, it has a loop. Okay, so from A to B, and then from B to C to D, and then go to E, and go to B again. Okay, so it will go like that. Okay, so this is called the hysteresis loop. 那我们可以怎么用啊？就是我们的 hard disk. Okay, so for us, 我们的硬碟，当然不是那个 SSD 了 ，SSD 是另外一个固态的电路嘛。那so for the hard disk, okay, actually we use the magnetic this ferromagnetic material to store the memory. Okay, so which is like so you have the disk, okay, and then you try to rotate to a certain position, and then you apply some external B field to it, okay, and then this is to write 1 or 0 to it, okay, to write a 1, okay, to write a 1 to a certain position, and then after you remove the external B field, it store a 1 there, and then maybe later you can just try to read, okay, whether this is a positive or a negative value, to say, okay, this is writing a 1 or writing a 0 in the hard disk, writing a 0, and then you try to read, okay, read a 0 read, okay, this is try to read a 1 from a hard disk. Of course, this case is slow, okay, for this mechanism is slow, so you need to rotate the disk to a certain position, and then you try to apply the B field to write a binary, and then also later on you need to rotate to that specific position to read the B field to see whether it's a 1 or 0 at that position. That's how the hard disk work. Or even though before, of course, maybe you have not seen that. Okay, the floppy drive, the 3.5 inch or even 5.25 inch floppy drive 就是那些3又1/2寸跟5又1/4寸的那个软磁盘 ，OK， 软磁碟 ，OK。So probably like 30 years ago, okay. So a computer still have the floppy drive. Probably you have never seen that. Okay, so this is the ferromagnetic material for the hard disk. Okay, so it can be used for some magnetic storage. Of course, it's not fast. Okay, so now we have something like the solid state circuit, solid state disk. Okay, SSD. Okay, if you are interested in constructing your computer, yes, probably you know.